Welcome back, everybody. Learning is a hobby here. In this video, I'm going to do section 1 in chapter 3 of Terence Tao's book analysis 1, which is on chapter 3 is on set theory, or I guess like basics of set theory. He develops a subject through an axiomatic system. Um, uh, I'm going to do the summary for section 3.1 here, but remember, I always say, you should read the book yourself, because my videos here are just a summary. They're just a skeleton of the chapter, so you'll be missing a lot of the flavor of the actual book, and what Terry Tao's personality is if you don't read the section yourself. But I'll go through the summary here. There's a bunch of exercises for section 3.1, which I haven't even attempted yet. So that video should not be coming out this weekend, but maybe next weekend. So it'll be a little while before I get around to the exercise set. But I have the summary at least here for you today. And it's kind of a long section, so just bear with me. I'll bring up my notes and then we'll go through everything one by one like we usually do. All right, so here we go. This is section 3.1. Like I said, it's on set theory. All right, so we start with an informal definition of what we mean by a set. So we define a set A to be any unordered collection of objects. If X is an object, we say that X is an element of A, or the symbol that denotes that is written here. That's read X is an element of A. If X lies in the collection, otherwise we say that X is not an element of A. And we start right off the bat with our first axiom. So the first axiom says that sets are themselves objects. So if A is a set, then A is also an object. In particular, given two sets, A and B, it is meaningful to ask whether A is also an element of B. Right? He has also so he numbers everything. I forgot, because it's been a while since I did chapter 2, but he even numbers his remarks and his examples and so on. So example 3.1.2, he has given here. He says informal for this. So the set containing the number 3, the set 3, 4, and the number 4 is a set of 3 distinct elements. So this is a set that also happens to have a set as an element. Okay, here he labels this this little discussion here as remark 3.1.3. There's a special case of set theory called pure set theory, in which all objects are sets. For example, 0 you can define as the empty set. 1 is the set containing the empty set. 2 is the set containing 0 and 1, or in other words, the set containing the empty set as an element, and the set containing the empty set as an element, etc. We can keep, go on like this. From a logical point of view, pure set theory is simpler, since everything is a set. But from a conceptual view, however, it's often easier to deal with impure set theories, in which some objects are not considered to be sets. So for the purposes of doing mathematics, the two are more or less equivalent. In this book, we take the impure view. We will not insist that natural numbers like 3 be identified with sets, but for us, natural numbers can be the cardinalities of sets. Now, we don't talk about cardinalities of sets in section 3.1. That's done later on in the chapter, so we'll get to that eventually. But you guys probably know what cardinality of a set means at this point, at least for finite sets. Hopefully you do. But anyway, we'll define it later on in the chapter anyway. Okay, that brings us to the next axiom. So axiom 3.2 is on equality of sets. So what do we mean when we say two sets are equal? Two sets A and B are equal, and we write that as A equals B like this, if and only if every element of A is an element of B and vice versa. To put it another way, A equals B if and only if every element X of A also belongs to B, and every element Y of B also belongs to A. All right, and he gives an example here. So notice that order doesn't matter and repeats don't matter in terms of equivalence for sets. So for example, the set containing 1, 2, 3, 4, 5 is the same thing as the set containing 3, 4, 2, 1, 5, and both of those are the same thing as the set containing 3, 3, 1, 5, 2, 4, 2. So even though they're repeats and the order is different, all three of these sets satisfy axiom 2, so they're by axiom 2 they're considered to be equal as sets. Okay, just a note here. The quote is an element of relation, which we denote by that symbol, that little like E, that weird looking E. Obeys the axiom of substitution, CA7. I talk about the axiom of substitution in the previous video, so I already posted the video for appendix section 7 on the channel. So if you don't know what the axiom of substitution is, you can watch that video. Because of this, any new operation we define will also satisfy the axiom of substitution, provided that it can be defined purely in terms of the is an element of relation. This will be the case with all new definitions in this section. Just to give a counterexample, I guess, an non-example, the operation does not satisfy the axiom of an operation that does not satisfy the axiom of substitution is the operation of, quote, first or quote, last element. For example, if you look at these two sets, the set containing the numbers 1, 2, 3, 4, 5 is equivalent to the set containing 5, 4, 3, 2, 1. Right, they're equivalent as sets. However, notice that the two sets have different first elements. So that would be an operation that doesn't satisfy the axiom of substitution. Right, axiom 3.3 next. This is the existence of a set that we call the empty set. So there exists a set that we denote like this. Again, you guys are probably familiar with that notation, known as the empty set, which contains no elements. So for example, for every object X is not an element of the empty set. Just a note here, this is about notation. The empty set is sometimes also denoted by the set brackets with nothing in between them. Right, so sometimes you'll see one, sometimes you'll see the other. Okay, now when I write something like this where I say proposition and notice that it's not numbered, Tao always numbers his propositions. In my notes here, when you see something like this where it just says proposition, what I'm doing is sort of answering a question from the book. So for example, just switching over to the actual book here, notice, for example, over here, there's, so in remark 3.1.9, he says, just as there's only one empty set, there's only one singleton set for each object A, thanks to definition 3.1.4, and he asks why. Whenever he does this in the book, I always write it down as a proposition and then I prove it. And you should get into the habit of doing that too, because when an author in a math textbook, says such and such is, trivial, or such and such is obvious, or this thing should be shown by the reader, or anything like that, or like if they ask why, you should stop what you're doing and actually do that. So actually figure out why it's true, and so that's what, when you see in my notes, if it's written like this proposition with no numbers after it, then this is sort of me answering a question that he asked in the text proper. All right, so here's the proposition. There's only one empty set. Okay, so here's my proof. Assume that, oops, I just dropped my pen. Sorry, just give me 1 second. I gotta grab it. All right, so assume that the empty set and this other set, which I'm calling, maybe I'll call it phi prime, are both empty sets. Assume that phi is not equal to phi prime, then without just loss of generality because of symmetry, there's some x in the set phi prime such that x is in, this should be not in. Sorry, let me just fix this. Okay, there's some x in phi prime such that x is not in phi. However, this contradicts that phi prime is empty, therefore phi is equal to phi prime by axiom 3.2. Okay. So that's like I said, when he asks why, I prove it. All right, the next thing is he calls lemma 3.1.5, and he labels this as single choice. Let A be a non-empty set, then there exists an object X such that X is an element of A. And here's my proof. I've said this in chapter when I went over chapter 2 also. I always do the proofs myself first. So some of the proofs that you'll see here are not necessarily the same as the ones that you'll see Tao use, but they should be valid. If you see any mistakes in them, let me know. But I always try, and you should too. I always try to prove things myself before looking at the author's solution. So here's my proof. Let A be a non-empty set. Assume for the sake of contradiction that for all objects X, where X is not an element of A, then X is an element of A if and only if X is an element of the empty set. Therefore, A equals the empty set by axiom 3.2. This contradicts that A is non-empty. All right, so that's called a single choice. It's a lemma, I guess. It's not an axiom, but it follows from one of the axioms. And then we're that, just to remind you, that's called single choice. He has a little remark here about finite choice and infinite choice, which we need another axiom for. So I'll just read this out here. Remark 3.1.6. Later on in lemma 3.5.11, we will show that given any finite number of non-empty sets, A1 through AN, it's possible to choose one element X1 through Xn from each set A1 through AN. This is known as finite choice. However, to choose elements from an infinite number of sets, we need an additional axiom, which is called the axiom of choice. You may have even heard of that before because it's an important axiom, which will be discussed in section 8.4. So, like I said in the previous video for Tao, I want to get through chapter 8 in his book too. So because that's later on down the line in the book, I just decided I'm probably going to just finish at least volume 1 of Tao's book. Not before I finish Spivak, but eventually I'll finish both of them. So here's remark 3.1.7. Note that phi is not necessarily the same thing as the number 0. Phi is a set and 0 is a number. Remember, we're assuming the non-pure version of, or a non-pure version of set theory. However, the cardinality of the empty set is 0. Cardinality of a set will be discussed later on in section 3.6. So we'll hold off on talking about cardinalities until that. But anyway, here the remark is making the distinction between 0 being a number, not a set, as far as we're concerned. So a 0 is an object, and it's not a set. However, the cardinality of the empty set can be represented by the number 0. Right, next axiom 3.4, singleton sets and pair sets. If A is an object, then there exists a set. This is the singleton set containing the object A, whose only element is A, i.e. for every object Y, we have Y is an element of A, the set A. Y is an element of the set containing A if and only if Y is equal to A. We refer to the set containing A as the singleton set whose element is A. Furthermore, if A and B are objects, then there exists a set, which is the pair set containing the objects A and B, whose only elements are A and B, i.e. for every object Y, we have Y as an element of the set containing A and B if and only if Y equals A or Y equals B. We refer to the pair set AB as the pair set formed by A and B. All right, so that axiom tells us that there exist such things. Remark 3.1.8 is next. The singleton set axiom is in fact redundant, being a consequence of the pair set axiom. Conversely, the pair set axiom will follow from the singleton set axiom and pairwise union axiom below, lemma 3.1.12. The pairwise union axiom will make the need for a triplet axiom or a quadruplet axiom, etc., unnecessary. I didn't finish that sentence, did I? The pairwise union axiom will make the need. Will make the need for defining those types of things. I'll just say I'll just say unnecessary, just to be proper English. the above remark follows from the following. So again, here's a proposition that I'm writing down here. But again, this is not written as a proposition in the chapter. He states this, and then he just asks the reader to say why. So here's the proposition for each object A. There's only one singleton set containing A, namely the set containing the object A. So here's my proof. Let A be another singleton set containing A, and take X in the set A. Then X equals A. So X is an element also of the singleton set containing A. Similarly, X, an element of the singleton set containing A, implies X equals A, and therefore X is also an element of the set A. Then that means that A equals the singleton set containing A by axiom 3.2, by equality of sets. Right. So here's another proposition that he states without proof, and he asks the reader why. So again, I'm writing it as a proposition and then proving it. So given any two objects A and B, there's only one pair set formed by A and B. Let A be another, here's my proof, let A be another pair set formed by objects A and B. Choose X in the element, I'm getting tongue-tied here. Choose X in the pair set containing A and B. Then X equals A or X equals B. That implies that X is also an element of A. Therefore, A equals, sorry, did I skip something here? Let A be another pair set. I think I skipped over one of the lines. Hang on. Let me read this over. Let A be another pair set formed by objects A and B. Choose X and A, then X equals A or X equals B. Either way, X is an element of the pair set A, comma B, containing A, comma B. Similarly, if X is an element of the pair set containing A and B, then X equals A or X equals B, so X is an element of A. Therefore, A is equal to the pair set containing A and B by axiom 3.2. Right, another proposition that Tao just states and asks why. If A and B are objects, then the set containing A, B equals the set containing B, A, the pair sets. Here's my proof. This follows directly from the previous proposition. So, you can think of like the pair set B, comma A as being the set capital A in the previous proof. Right, another statement that he asks the reader to prove. So if A is an object, then the set containing the element A, comma A, equals just a singleton set containing A. And here's my proof. If X is an element of the singleton set containing A, then X equals A. So X is an element of the set containing A, comma A. Also, if X is an element of the set containing A, comma A, then obviously X is A. Therefore, X is an element of the singleton set containing A, and therefore by axiom 3.2, the two sets are equal. All right, he gives another example here as well. Since the empty set is a set, if it's an object, then the following are also sets and are not equal. He says here, see exercise 3.1.2. So I guess he'll ask us to prove this in that exercise. But here he's just listing them. So since the empty set is itself a set, and that means it's an object, which means it can be an element of other sets. So for example, these three examples that we have here are also sets. So the set containing the empty set is a set. The set containing the empty set is a set. The set containing the empty set and the set containing the empty set is also a set, and so on. Okay, so here's the next axiom, axiom 3.5. This is called pairwise union. Given any two sets, A, comma B, there exists a set which we read A union B. That's called the union of A and B, which consists of all the elements which belong to A or B or both. In other words, for any object X, if X is an element of A union B, if and only if X is an element of A or X is an element of B. And just a note, I think I probably have mentioned this before in some other video, but in mathematics, or the word or always means the inclusive or unless otherwise specified. And he says here, see the appendix section 1, because that's where we talk about logic, the logical operators. I posted the video for the appendix section 1 on the Patreon page. I'm not going to post it here. So if you want to see that, you can join the Patreon page. I did the solution set to A1 to appendix A part 1 also. There and now I've also posted section A7 on the channel proper, along with its solutions to its exercise set. So really the only thing I still have to do in appendix A are the intermediate sections, section 2 to 6, which I'll post to the Patreon page eventually. There's no exercise sets for those, so that'll just be like a summary of the stuff there. And what he talks about in those sections is just logic and proof techniques and so on. Okay, example 3.1.10. Again, just an example here of union. The pair set containing 1 and 2, union the pair set containing 2 and 3, is equal to the set containing 1, 2, and 3. And you can prove that by using axiom 3.2 if you like. Okay, remark 3.1.11. The operation of union obeys the axiom of substitution and is therefore well defined on sets. So here's another proposition. If A, B, A prime, B prime are sets where A equals A prime and B equals B prime, then A union B equals A prime union B, and A union B equals A union B prime. So in other words, in this proposition, Tao is asking the reader to prove that union, the operation of union is well defined. Okay, so here's my proof. Let X be an element of A union B, then X is an element of A, or X is an element of B. That's just from the definition. If X is an element of A, then X is an element of A prime, since A equals, sorry, did I mean A prime here? X is an element of A, then X is an element of A prime. This should be A prime here, I think. This is a typo, since A equals A prime. So X in A prime or X in B implies X is an element of A prime union B. A similar proof shows that X is an element of A prime union B implies X is an element of A union B. Therefore, the two sets are equal by axiom 3.2. And a similar argument, I guess I just didn't feel like writing this whole thing out because it's very similar. A similar argument shows that B equals B prime implies A union B equals A union B prime. Okay, going on to the next lemma. This is lemma 3.1.12. If A and B are objects, then the pair set formed by A and B is equal to the union of the singleton sets containing A and containing B. If A, B, C are sets, then the union operation is commutative associative. Also, we have A union A equals A union the empty set equals the empty set union A equals A. So there's a bunch of things here that this lemma states, and we'll just prove them one at a time. So here's my proofs. I think actually, now that I'm remembering when I went over this, the only thing he proves actually in the book, let me just mark this. In the chapter, in the section 3.1, Tao only proves this one, and I think he leaves the other ones for exercises, but I didn't realize that until afterward. So I ended up proving these. So we'll just skip over that exercise when we get to the exercise sets. But let's look at the proofs of all of these. All right, so property 1, the pair set containing A and B equals the union of the singleton sets containing A and B. So here we go. Let X be an element of the union, then X is an element of A, or X is an element of B. That's just by the definition. And that implies that X equals A or X equals B. Since the union of the singleton sets containing A and B is a pair set containing A and B, and because that's a pair set containing A and B, then the union of the singleton set A containing A and B, sorry, I'm getting tongue-tied here, equals the pair set formed by A and B by uniqueness of pair sets, which is something that we proved a little while ago. All right. Property 2 is the commutativity. So we want to show that A union B is B union A. So here's my proof. If choose X to be an element of A union B, sorry, let me just state it so I can say the if and only if here in proper English. X is an element of A union B if and only if X is an element of A, or X is an element of B if and only if X is an element of B, or X is an element of A, right? The English word or doesn't care which one you say first. Implies X, this should be if and only if. Just fix this. This should be double arrow. If and only if X is an element of B union A. So that proves that one. 3 is the associative property. And like I said, he actually proves this one in the book, but like I said, you should always do your proof before looking at the author's proof. So here's mine. X is an element, if, sorry, X is an element of A union in parentheses B union C if and only if X is an element of A, or X is an element of B union C. If X is an element of A, then X is an element of A union B implies X is an element of A union B union C, where A union B is in parentheses first. If X is an element of B union C, then X is an element of B, or X is an element of C. If X is an element of B, then X is an element of A union B, which implies that X is an element of A union B union C. If X is an element of C, then X is an element of A union B in parentheses union C. And a similar argument shows that associativity the other way works. So I just skipped showing that because it's exactly analogous to what we did. All right, property 4. There's actually a few equalities that he asks us to prove. Part A says A union A is equal to A. So here's my proof. X is an element of A union A. It implies that X is an element of A, or X is an element of A, which means that X is an element of A. Also, X is an element of A implies that X is an element of A union A, so that shows that the two sets are equal. All right. Similar kind of things for the other ones too. A equals A union the empty set. So let's prove that. X is an element of A implies X is an element of A, or X is an element of the empty set. Remember, the empty set has no elements, so X an element of the empty set is sort of like trivial. Implies X an element of A union the empty set. Also, X an element of A union the empty set implies X is an A, or X is an element of the empty set. Since the empty set has no elements, that means that X has to be an element of A, since the empty set is empty. And that implies that A equals A union the empty set. And then part C, we want to show that A union the empty set is the same as the empty set union A, but this follows directly from commutativity, which we showed in part 2. So that's the proof. Okay, just a note here, because union is associative, we need not use parentheses in expressions of unions of more than two sets. So in other words, A in parentheses, A union B union C is the same thing as just A union B union C, which is the same thing as A union and then in parentheses B union C. So you don't have to worry about parentheses for unions. Same thing for intersections. We haven't gotten up to intersections yet, but that's also an associative operation. Okay, remark 3.1.13. While union and addition have some similarities, they're not the same. So in a lot of these remarks, what Tao does is sort of show you common pitfalls. So while the union of the singleton sets containing 2 and 3 equals the pair set containing 2 and 3, and 2 plus 3 equals 5, the sum of the singleton sets containing 2 and 3 is meaningless. So addition is an operation that we define on numbers, not on sets. Similarly, 2 union 3 is meaningless since union is an operation that we perform on sets, not numbers. And remember, we said that we're going to assume that numbers are not sets. We're not working in pure set theory. Okay, here's a note by the lemma. The triple set, I guess you could call it, containing A, B, and C is equal to the triple union of the singleton sets containing A, B, and C. And same thing for the set containing 4 elements and so on. So those two things follow from the above lemma. However, we're not yet in a position to define sets containing n objects for any n natural number, since the concept of n-fold iteration of the above construction has not yet been rigorously defined, but we will do that later. Furthermore, infinite iteration of pairwise union is required for the construction of infinite sets. In the infinite case, we will eventually introduce other axioms of set theory, which will allow us to construct arbitrarily large and even infinite sets. To formalize the concept that some sets appear to be larger than others, we introduce the concept of subsets next. So here's the definition of a subset. This is definition 3.1.14. Let A and B be sets. We say that A is a subset of B, denoted this way. That means A is a subset of B if and only if every element of A is also an element of B, i.e. for any object X, if X is in A, then X is in B. And we say that A is a proper subset of B, denoted by this symbol here. So this is read A is a proper subset of B. If A is a subset of B and A is not equal to B. Right, so that's our definition of subset. Again, a lot of remarks and stuff here. We're just introducing all these concepts, so there's a lot of talking before we get to do things. But we have to define stuff. And like I said, in these remarks, he's sort of outlining common pitfalls, so they're worth reading out. Because these definitions involve only the notion of set equality and quote unquote is an element of, both of which obey the axiom of substitution, the notion of subset also obeys the axiom of substitution, meaning it's well defined. For instance, if A is a subset of B and A is equal to A prime, then A prime is a subset of B, and he illustrates that with an example here. I won't belabor that. You could look at the example. Here's a proposition. So again, this is something where he just states something and asks the reader why it's true. So I'll prove it here. So given any set A is a subset of itself. Right, so here's my proof. Let A be a set, then if X is an element of A, obviously X is an element of A, and that implies that A is a subset of A. It satisfies the definition. Okay, there's another proposition that he states without proof, and he asks you why. For any set A, the empty set is a subset of A, and here's my proof. Since the empty set is empty, it is vacuously true that X in the empty set implies X is an element of A. Therefore, the empty set is a subset of any set A. Okay, just a note, the it's a subset of symbol is similar to the notion of less than or equal for numbers, but it's not necessarily the same as that, but it is similar. We'll see how they differ in a minute. Here's a proposition. Sets are partially ordered by set inclusion. So here's what that means. Let A, B, and C be sets. If A is a subset of B and B is a subset of C, then A is a subset of C. Also, if A is a subset of B and B is a subset of A, then A equals B. Finally, if A is a proper subset of B and B is a proper subset of C, then A is a proper subset of C. So there's three statements there, and I prove them one at a time. All right, so here's my proof. For part one, let A, B, and C be sets such that A is a subset of B and B is a subset of C. Then if X is an element of A, that means that X is an element of B because A is a subset of B. Since X is an element of B and B is a subset of C, that means that X is an element of C. Therefore, A also has to be an element, has to be a subset of C. All right, going on to statement two, let A be a subset of B and B a subset of A. Then if X is an element of A, X is an element of B because it's a subset. Also, Y an element of B, then Y is an element of A because B is a subset of A. Therefore, A equals B by axiom 3.2. All right, and then finally, the third statement, let X be a proper subset of B and B a proper subset of C. From part one, it's clear that A is a subset of C, right? The subsets move transitively through the chain, I guess. Assume for the sake of contradiction that A is equal to C. Then if Y is an element of C, Y is an element of A implies Y is an element of B. Since A is a subset of B, this implies that C is a subset of B, which implies that B equals C, and that contradicts that B is a proper subset of C. Right, and that's my proof. Okay, remark 3.1.18. See exercise 3.1.7 to see that the union operation and subset operation are related to each other. So we'll have to wait till I get around to the exercise sets to see that. remark 3.1.19, there's an important difference between, so here's what I was saying about there's a difference between the two. They're not exactly, even though there's similarities, they're not exactly the same. There's an important difference between is a proper subset of and strictly less than. While any two distinct natural numbers n m satisfy n less than m or m less than n, it is not the case that for any two distinct sets a, b, that a is a proper subset of b or b is a proper subset of a. For example, a equals a set to n such that n is an integer, and b equals the subset, sorry, and b equals the set of all 2n plus 1 such that n is an integer, satisfy neither a is a proper subset of b or b is a proper subset of a, because of this we say that sets are partially ordered, whereas the natural numbers are a totally ordered set. And these things are defined actually in chapter 8, so we'll have to wait till chapter 8 to look at the formal definitions for that. Okay, another remark. Is a subset of is not the same as is an element of. So again, this is a common error that people make. For example, 2 is an element of the set containing 1, 2, and 3, and the singleton set containing 2 is a subset of the set containing 1, 2, and 3. But the singleton set containing 2 is not an element of the set containing 1, 2, and 3, and 2 is not a subset of the set containing 1, 2, and 3. So it's important to distinguish sets from elements as they may have different properties. For example, the natural numbers is an infinite set whose elements are finite numbers, whereas the set containing the set of natural numbers, set of integers, set of rationals, set of real numbers is a finite set, has 4 elements in it, right? Whose elements are infinite sets. Okay, the next axiom allows us to create subsets out of larger sets. This is called the axiom of specification. All right, so let's read it out. Let A be a set, and for each x in A, let P of x be a property pertaining to x. For example, for each x in A, P of x is either a true statement or a false statement. Then there exists a set called the set of all x in A, such that P of x is true, or simply, it's sometimes written more compactly like this, the set of all x in A such that P of x, whose elements are precisely the elements x in A for which P of x is true. In other words, for any object y is an element of the set of all x in A such that P of x is true, if and only if y is an element of A and P of y is true. Right, so that's called the axiom of specification. So here's a note. This axiom is also known as the axiom of separation, so you might see it written in other books that way. Particularly, I think Patrick Soup's book, I think, refers to it as the axiom of separation. I might be wrong about that, but I'll talk about Patrick Soup's book on set theory maybe at some point in the future. Okay, another proposition that Tao just says as a statement and asks you to prove it. The set of all x in A such that P of x is true is always a subset of A. So here's my proof. If P of x is false for all x in A, then the set of all x in A such that P of x is true is the empty set, and that's a subset of any set. So in particular, it's a subset of A. If P of x is true for at least one x in A, then y, an element of the set x, the set of all x in A such that P of x is true implies y is an element of A. Therefore, the set is a subset of A. And that's the proof. Right? Another proposition that he states without proof, the x, and just labeling it here, the axiom of substitution works for specification. If A equals A prime, then the set of all x in A such that P of x is true is equal to the set of all x in A prime such that P of x is true. So in other words, what he's saying is the axiom of specification is well defined for sets. So let's look at our proof here. So take x, an element of the set of all x in A such that P of x is true. That's a subset of A, which is equal to A prime by hypothesis, implies that x is an element of the set of all x in A prime such that P of x is true, which implies that x is an element of A such that P of x is true is the subset of the set of all x and a prime such that p of x is true. And I won't show the other way because it's just a similar thing, just done in the opposite order. A similar argument shows that x, an element of a prime, the set of all x in a prime such that p of x is true is a subset of the other set. Therefore, the two sets are equal by axiom 3.2. Okay, here's another example that he gives. This is example 3.1.21. Let S be defined to be the set containing 1, 2, 3, 4, 5. Then the set containing n in S such that n is less than 4 is the set of those elements n in S for which n is less than 4 is true. For example, the set of all n in S such that n is less than 4 is equal to the set containing 1, 2, and 3. Similarly, the set of all n in S such that n is less than 7 is equal to S, and the set of all n in S such that n is less than 1 is the empty set. Okay, we have a note here. Sometimes we write the set of all x and a such that p of x with a line rather than the colon. Sometimes we do that if if we're using a colon to represent some other thing. So just so it's not confusing. The axiom of specification can be used to define some further operations on sets. For example, intersection and set difference. So we'll define those next. Like I said, this is kind of a long section. This is definition 3.1.22. This is the definition of intersection of two sets. So the intersection S1 intersect S2 of two sets is defined to be the set S1 intersect S2, that's defined to be the set of all x in S1 such that x is in an element of S2. In other words, x is an element of S1 intersect S2 if and only if x is in S1 and x is in S2. Right, that's the definition. Here's a remark. Because intersection is defined in terms of more primitive operations that satisfy the axiom of substitution, it also satisfies the axiom of substitution. Therefore, intersection is well defined. The same will be true of the rest of the definitions in the chapter and will no longer be mentioned specifically. So, but just be aware that all these operations can be shown to be well defined. They all satisfy the axiom of substitution. Okay, so here's again some examples of intersections. I won't read them out. You could read it here. I don't want this video to be too long, but these are some examples of intersections of sets. Actually, one of them is a union. The third one, the pair set containing 2, 3 union. The empty set is just a pair set containing 2, 3, and the other 3 are intersections. Okay, remark 3.1.25. One reason we resort to mathematical symbols instead of English words like and is that mathematical symbols have a precise, unambiguous meaning, whereas one must look very carefully at the context in order to work out what the English word means. For example, depending on the context, and can mean union or it could mean intersection. Sometimes and is also used for addition, so that's why mathematical symbols are important because they're unambiguous and precise. All right, just a note here, two sets A and B are said to be disjoint if A intersect B is empty. Note that this is not the same concept as being distinct, which means that A is not equal to B. For example, the two sets, the set containing 1, 2, 3 and the set containing 2, 3, 4 are distinct, but they're not disjoint because they have non-empty intersection. Right, the intersection is the pair set containing the numbers 2 and 3. Again, here's a proposition that he states that he wants us to prove. The sets the empty set and the empty set are disjoint but not distinct. So here's my proof. If you take the intersection of the empty set with the empty set, you obviously get the empty set. However, the empty set is equal to the empty set, so it's not distinct. The next operation on sets is somewhat analogous to subtraction. We haven't defined subtraction formally yet, but anyway. We will when we get to the integers, I believe, the set or the chapter where we construct the integers. Definition 3.1.26, different set of sets. Given two sets A and B, we define the set A minus B, or sometimes it's more commonly written like this, A slash B, which it means set difference, to be the set A with any elements of B removed. So the set difference of A with B is defined to be equal to set of all X in A, such that X is not an element of B. And just a note, in many cases, B will be a subset of A, but it doesn't necessarily have to be. So for example, here, the set containing 1, 2, 3, 4 minus the set 2, 4, 6 is equal to the pair set containing 1 and 3. Right, another proposition that whose proof he leaves for the reader to do in the exercise set, but we'll read out the different parts to it. So this is proposition 3.1.27. Sets form what's called a Boolean algebra. Let A, B, and C be sets, and let X be a set containing A, B, C as subsets. So X is sort of like a universal set, and the sets A, B, and C are, just general subsets of the universal set. Okay, part A, minimal element. We have A union the empty set equals A, and A intersect the empty set is the empty set. We have part B, maximal element. A union X equals X, and A intersect X equals A. The next property, part C, is called identity. We have A intersect A equal A, and A union A equals A. We have commutativity of union and intersection. We also have associativity of unions and intersections. There's a distributive law, so just intersections distribute over unions, and unions distribute over intersections. Part G, we have something called partitioning. We have A union, the set difference X with A equals X, and the intersection of A with the set difference of X with A is the empty set. Part H is called De Morgan's laws. We have the set difference of X with A union B is equal to the intersection of the set difference of X with A and the set difference of X with B. And the set difference of X with A intersect B is equivalent to the union of the set difference of X with A and the set difference of X with B. And like I said, the proof of this is left as an exercise, so that we'll get around to this when we get to the exercise set. All right, just a remark. De Morgan's laws are named after the logician Augustus de Morgan, who lived from 1806 to 1871, who identified them as one of the basic laws of set theory. All right, another remark here. The symmetry in the above laws between union and intersection, as well as X in the empty set, is an example of what's called duality, two distinct objects or properties being dual to each other. In this case, the duality is manifested by the complementation relation. So in other words, A is taken to X minus A. The De Morgan laws assert that this relation converts unions into intersections and vice versa. It also interchanges X with the empty set. And then just a note of about where the name comes from. The above laws are known as the laws of Boolean algebra, after the mathematician George Boole, who lived from 1815 to 1864, and are applicable to other objects than sets as well. But they apply to sets here, which is what we're interested in. They're particularly important in mathematical logic. Now, one of the things we are not yet able to do is to take each of the objects in the set and transform them into a new object. Into new objects. We need a new axiom for this, which we'll talk about here, which is called the axiom of replacement. This is axiom 3.7. All right, replacement says, let A be a set for any object X and A and any object Y. Suppose we have a statement P, X, comma, Y pertaining to X and Y, such that for each X and A, there's at most one Y for which P of X, Y is true. Then there exists a set of, which we're giving the name here, this is the set of all Y such that P of X, Y is true for some X in X an element of A. Such that for any object Z, Z is an element of the set Y such that P of X, Y is true for some X in A, if and only if P of X, comma, Z is true for some X in A. All right. So here's an example just illustrating that axiom. So let's say we define the set A to be the set containing 3, 5, 9, and let P of X, Y be the successor operation. So P of X, Y is defined to be X. This is the successor of X. Note that in this case, for each X in A, the successor of X is unique. We talked about this way back in chapter 2. Therefore, by the above axiom, the set of all Y such that Y is the successor of X for some X in the set containing 3, 5, and 9 exists. And then there's some propositions that he states again that he wants us to do ourselves. So here's the first proposition. the set of all y such that y is the successor of x for some x in the set containing 3, 5, 9 is equal to the set containing 4, 6, 10. So here's my proof. So let y be an element of that set, of the first set. Then y is the successor of 3, which is the same thing as 4, or y is the successor of 5, which is equal to 6, or y is the successor of 9, which is 10. Therefore, y is an element of the set on the right. Similarly, if y is an element of the set on the right, then y equals 4, which is the successor of 3, or y is 6, which is the successor of 5, or y is 10, which is the successor of 9. Therefore, y is an element of the set on the left. Therefore, the two sets are equal by axiom 3.2. Okay, example 3.31. Let A be the set containing 3, 5, 9, and P of xy be the statement y equals 1. Then for each x in the set A, there's exactly one y that makes P of xy true, namely y equals 1. Therefore, the set of all y such that y equals 1 for some x in the set 3, 5, containing 3, 5, 9 is equal to the singleton set containing 1. So this example just shows that with that axiom, sometimes you'll get sets that are smaller than the original set. So that's possible. Okay, so oftentimes we abbreviate that set there, the set of all y such that y equals f of x for some x in A, as the set of all f of x such that x is in A, or sometimes instead of the colon, we use the vertical line. Okay, here's another note. We can combine the axiom of specification and the axiom of replacement. For example, we can create the set that we have written here, the set of all f of x such that x is in A and p of x is true, by starting with the set A, applying the axiom of specification to obtain the set of all x in A such that p of x is true, and then applying the axiom of replacement to obtain the set of all f of x such that x is in A and p of x is true. And just an example, showing that here we have the set of the successor of n such that n is an element of the set 3, 5, 9, and n is less than 6. That's equal to the parish set containing 4 and 6. Right, and now we want to formalize our assumptions that the natural numbers are objects. This is called the axiom of infinity. There exists a set n whose elements are called natural numbers, as well as an object 0 in n and an object that we call the successor of n assigned to every natural number n in n, such that the piano axioms, if we remember, we went over the piano axioms in chapter 2. It was axioms 2.1 to 2.5. So such that the piano axioms hold. All right, just a note also, this is a more formal statement of assumption 2.6, which was done at the end of chapter 2. Was it the end of chapter 2? I forget when we did that, but you could look back at the videos. It is called the axiom of infinity because it introduces the most basic example of an infinite set. The meaning of finite and infinite will be formalized in section 3.6. So now we know from the axiom of infinity that numbers such as 3, 5, 7, etc. are objects. Therefore, we can legitimately construct sets like the set containing 3, 5, and 7. And again, he gives a caution here. The set n plus 3, the set of all n plus 3 such that n is a natural number and n is greater than or equal to 0 and less than or equal to 5 is not the same thing as the expression n plus 3. So you need to keep the concept of a set distinct from the elements of that set. So again, this is a common mistake that people make. So he's just stating this explicitly as a caution. Okay, example 3.1.32, he labels this as informal. This example involves the notion of subtraction, again, which has not yet been formally introduced. We'll do that later on, like I said, when we get to the integers, I'm sure. So the set of n plus 3, the set of all n plus 3 such that n is a natural number and n is greater than or equal to 0, less than or equal to 5 is equal to the set of all 8 minus n such that n is a natural number and n is greater than or equal to 0 and less than or equal to 5, even though the expression n plus 3 and 8 minus n are never equal for any n in the natural numbers. right? And there's some propositions here. So first I show that the set of all eight minus n, such that n is a natural number, and n is greater than or equal to 0, less than or equal to 5, is equal to the set of all 8 minus m, such that m is a natural number, and m is greater than or equal to 0, less than or equal to 5. Both sets, so here's the proof. Both sets are actually equal to the set containing 3, 4, 5, 6, 7, 8, which you can show. Right? Then the set of all n plus 3, such that n is a natural number, and n greater than or equal to 0, less than or equal to 5, is equal to 8 minus m. Is equal to the set of all 8 minus m, such that n is an element of the natural numbers, and n is greater than or equal to 0, less than or equal to 5. Should make the equality a bit easier to see. So just, writing them with different parameters. Note that n plus 3 is equal to 8 minus, in parentheses, 5 minus n, and m equals 5 minus n implies that for any, if n is greater than or equal to 0, less than or equal to 5, then notice if m is defined to be 5 minus n, then m is also greater than or equal to 0 and less than or equal to 5. Furthermore, 8 minus m equals 3 plus 5 minus m in parentheses, and n equals 5. Sorry, I'm losing my voice here now. N is equal to 5 minus n implies if m is greater than or equal to 0, less than or equal to 5, then also n is greater than or equal to 0, less than or equal to 5, if we define n to be 5 minus m. All right, is this the last thing? Yeah, okay. Yeah, like wore my voice out reading all that stuff. So here's the last note in section 3.1. Henceforth, we may have used language somewhat and refer to the natural numbers n as the natural numbers rather than the set of natural numbers, z as the integers rather than the set of integers, r as the real numbers or the reals rather than the set of real numbers, etc., etc. So we'll sometimes abuse language that way, is what he's saying in the book. So, okay, let me stop the screen share here. All right. So that's section 3. My summary for section 3.1. Like I said, you should actually read the section yourself and try, to do all the statement, prove all the statements and everything yourself. In the next video, I'll post my solutions to the exercise set for section 3.1, which should be sometime this week. Obviously, it's not going to happen tonight because I still have some stuff to do. But I'll see you guys in the next video. Let me know what you think down below, and I'll see you in the next video.